Yeah, ladies and gentlemen, welcome to AU also from my side. I'm really thrilled to be here with all of you, our customers and partners, and with all this industry knowledge in this room, and your willingness to network and to learn from each other, that ultimately leads us to improve the way we do our work and also contribute to our joint vision to make a better world. Today I want to talk about Connected BIM and how technology will disrupt and transform the AEC industry in the era of connection. But before I do so, I would like to take a step back and look to a bigger picture. Significant technology changes have always changed the way we work. When you think about the first industrial revolution, it was watercraft and steam power that enabled productivity increases. In the second industrial revolution, it was the electricity that allowed for standardization and mass production. And in the third, we took advantage of information technology and electronics to drive automation. Now we are moving into the fourth industrial revolution, Industry 4.0. And this is characterized by a fusion of technologies. The boundaries between the digital, the physical, and the biological sphere will merge. And there are three reasons why this digital era is not just an extension of the third industrial revolution, but a new kind of revolution. These three things are the speed, the range, and the systemic effects that it covers. The speed by which we see technological breakthroughs has never been achieved before. Compared to other industrial revolutions, this revolution is developing exponentially, not with linear pace. And it affects all industries in all countries in the world. Think about the spread of mobile devices in the emerging countries. The opportunities of billions of people connected through mobile devices with unprecedented speed and capacity is unlimited, and so is the access to knowledge. And these opportunities are even exponentiated by emerging technological breakthroughs that we see coming, like artificial intelligence, robotics, 3D printing, additive manufacturing, bio-nanotechnology, material science, energy savings, or quantum computing with computing performance 100 million times faster than a usual laptop. And artificial intelligence is all around us. Think about self-driving vehicles, think about drones or swarms of drones that control themselves, or think about virtual assistants that can take decisions by themselves or prepare decision alternatives based on certain preconditions. The technological transformation is complex, and disruption is all around us. Think about TV, music streaming, shopping, or gaming. Each of these images on the screen symbolize somehow a little disruption that we face in everyday life. And we think about the explosion of information. It's changing anything what we understand about design and construction. Think about complex sensor systems that control the physical behavior of buildings. Think about microfactories that allow for off-site production. Or think about prefabricated elements that allow us to build more efficiently, with sensors built in that can be tracked, geolocated, linked to the cloud, back to the BIM model, and accessed from anywhere, anytime. By 2020, we will have 50 billion sensors and devices connected to the internet and producing huge amounts of data. Now, let's step back again and look to our industry. The digitalization in its basic form started 35 years ago, when we moved the design task from the drafting board to the computer. With products like AutoCAD, data formats like DWG, we achieved automation already. Everything was based on documents, therefore we call this the era of documentation. 15 years ago, we started to develop and implement BIM. building information modeling, allows us to generate geographic but also semantic information across the disciplines on one common platform and apply simulation and analysis software to simulate the physical behavior of these buildings before it's built. Through iteration steps, we are able to optimize this building. Therefore, we call this the era of optimization. And there are countless projects have been BIM used in the last 15 years during this era of optimization. And those customers who have already successfully implemented BIM experience huge benefits and competitive advantages today. And public and private clients are increasingly requiring the use of BIM processes. Many governments around the world also recommend or mandate the use of BIM in so-called BIM mandates or directives. In Europe, the United Kingdom is one of the pioneers, publishing really impressive numbers on return on investment of BIM, like 33% lower cost, 50% faster delivery, and they want to become the world leaders in BIM. There is a competition of the governments going on. But the challenges in front of us are huge. Our industry, the construction industry, contributes 10% of the gross world product. Our output today is $8.5 trillion, and in the next 12 years, we will double this output. This growth is coming from economic growth in general, huge investment in infrastructure, but, and Linnell has pointed this out, by population growth and urbanization. Today, we have 7 billion people living on the planet, half of them live in cities. By 2050, we will have around 10 billion people, but 7 billion people live in cities. That means that cities will grow with an impressive speed. We will need to add 2 million people every single week to cities. This means we need to double the city capacities within this time frame, which also means that we need to build 5,000 buildings every single day for the next 33 years to meet this demand. But all this under the dilemma of productivity problems that we have in our construction industry. For decades, we have been flat in productivity or even decreasing, where other industries have been increasing. Manufacturing has even doubled the productivity. A big reason for that is that our processes in our industry are still largely analog processes. But this is also underlined through studies like this, where the digitalization index shows that our industry is one of the last laggards, whereas manufacturing, for example, is one of the leaders. But this correlates also to IT investment of the past, right? Where investment in our industry was around 1.2%. Only agriculture and hunting is investing less in IT, while manufacturing is investing 3 times more. But this is currently changing. It will be significantly changing in the future. Big consulting companies like McKinsey or Boston Consulting have published studies where they found out that there is huge potential in efficiency gains and cost savings in our industry. By moving to a fully digitized process, we could save $1.2 trillion every year in our industry. And these studies also mention what areas need to be addressed in terms to leverage these effects like efficiency gains and cost savings. More or less, it's 5 things. It's high-density surveying and geolocation, integration in hardware. It's about adoption of BIM and also adding the 4D and 5D components to it. It's about digital collaboration, immersive visualization, and mobile computing. The 4th is Internet of Things. It's about advanced analysis. It's about machine learning and artificial intelligence. And the 5th is the democratization of new production methods like you have heard about 3D printing, additive manufacturing, or industrialized construction. Now, the good thing is, in the era of connection with Connected BIM, we are addressing all of these topics. With Connected BIM, we are using cloud, social, and mobile computing to drive the process from the design to fabrication to construction and operation holistically, with simultaneous involvement of economical factors and also environmental factors, taking into account also social aspects. Now let's look into some important things that is important for this. I think most important thing is to understand that Connected BIM, in easy words, is BIM plus the power of the cloud. Important components of Connected BIM is, for example, digital and symmetrical collaboration. Design and construction teams are complex and they are distributed around the globe in the different companies. By its heart, the collaboration in our industry is asymmetrical, with many different companies working on the same project on their own problem. But with Connected BIM, we are able to deliver a platform in the cloud where all this information can be collected and managed and made available for all stakeholders. At the same time, immersive visualization is being adopted with impressive speed across the teams. And also this will help to drive digital and symmetrical collaboration. Think about the discussion using VR between the design teams to explore a design, discuss a design, or to explain a design intent to an owner, or to explain a problem of constructability to a worker in the field. Immersive visualization, VR, AR, and mixed reality is an integral part of BIM in the cloud. In this example, an architect is explaining a design intent to an owner which sits 5,000 miles away using VR and the cloud technology. Cloud computing also enables and provides the ability to access literally unlimited computing power to every stakeholder in the project. What this means is that the most complex analytical problems can be solved nearly in real time. In this case, if the structural engineer changes the column of this structure, he will directly see the impact of the tension, the shear force, or the bending moment, and can react accordingly. He can also run through design iteration steps and optimize the design, or react to requests from his design teams and respond quickly in real time. But if you don't want to define the iteration steps yourself to optimize the building, because the building is too complex, the problem is too big, you can also use the computer to do so. By defining some rules of the construction project and constraints, the computer runs through iteration steps, hundreds and thousands of iteration steps, like Linnell showed before, until the best solution is found. Generative design is more or less a simulation of an evolution process that starts with the design and with the goals and constraints, and runs through permutations based on convergence criteria until the best solution is found. I don't want to show too many fancy projects. Linnell also mentioned already the Museum of the Future. This is an amazing project here in Dubai. And the design and construction team, they have really pushed the boundaries of what is possible in this project. The design intent describes an organic freeform shape. But in order to make this buildable, as our subject matter expert knows, it needs to be polygonized. The question is how to get close to the shape, how to reduce weight, how to reduce the number of different facade elements and the number of nodes, and how to respond to some sustainability requirements. I think you get the problem here. Our customer, Bureau Happold, they use generative design to optimize 3 areas. They were able to reduce the number of nodes by 40%, reduce the material weight by 30%, and get very close to the shape by reducing the deviance of the shape by 80%. Again, this project is amazing and meeting the highest quality and sustainability standards possible. You will hear more about this project directly from Bureau Happold later here on the stage. But data is really driving our design decisions more and more. Traditional methods are not able to handle this huge amount of data, and there is where machine learning comes into play. Machine learning is a kind of artificial intelligence that provides the computer with the ability to learn without being explicitly programmed for it. Computer learns just by being exposed to data. Imagine if you could feed this algorithm with project information and the system comes back to you with a design proposal because it looked to previous experiences, a design proposal that maybe avoids failures that have been made in the past. This is an example of advanced simulation analysis and also machine learning algorithm. It is called CrowdCloud. It's a research project that we are doing. So you can analyze crowd movement based on different stress factors, like fire, and then use the heat map to point out where the problem areas are. With the power of the cloud, the designer can directly see the impact if he makes changes to the layout. And the next step, we are using machine learning tools to find the right layout of a building based on a desired people movement. Now, let's talk about how generative design and machine learning can help us to optimize the process from design to fabrication and construction. And here we can learn from manufacturing and leverage and further develop concepts and methodologies like DFMA. DFMA stands for Design for Manufacture and Assembly and consists out of 2 different methodologies. Design for manufacture, which means to design for the ease of manufacture of parts that form the products. And the second is design for assembly, which means to design the products for the ease of assembly to bigger parts and to buildings. Now, AEC is an extreme form of mass customization, but if you really look into it, the majority of the buildings that we build, they have repetitive content. Schools, hospitals, hotels, data centers, office buildings. Think about big residential buildings with different apartment types. But we don't have a smart way to deal with this challenge in fabrication, in design, or in construction. When we want to respond to the demand of the future, think about the 5,000 buildings we need to build every day, getting more complex as they are part of a smart city concept, reducing the environmental footprint. We need and we must find ways to help the building design teams to build more standardized and modular, but customizable, and use this also and drive this also into fabrication and construction processes. Imagine if a smart assistant would help an architect or an engineer to focus their designs on the way the building will be delivered, built, and fabricated. A machine learning tool that would, based on project-specific input in combination with past experience, create a library of modules that are customizable, that optimize the spaces and logistics of buildings. It all could start with conceptual, parametric placeholders, very easy in geometry, but complex in data. You can easily use these modules then to optimize your designs, but also to enable early estimation or optimization of procurement. At later stages, you could then further detail these products, these modules, and detail the geometry, make it more precise, and also enrich information around supply chain. But this does not mean that all these modules need to be the same. At the contrary, these modules can be modified, they can be stretched, they can be mirrored, they can be configured, they can be adjusted. DFMA allows for mass customization at the same time streamlining the process from design to fabrication and construction. And individual modules could also be designed for flat pack delivery. These individual modules can then be combined to bigger multidisciplinary components that carry already fabrication logic and assembly instructions. And of course, also QR codes and sensors to track delivery on the building site. So now, how does the factory of the future look like? The AEC factory of the future. The make process is also going to change. These offsite factories, they will produce multi-material and multidisciplinary panels and modules all in one place. The machining process will be automated, following recipes and fabrication logic derived directly from the BIM model, which is DFMA enabled. And of course, all these elements will be equipped with QR code and sensors, so you can track them from design to fabrication and to delivery on site until installation at the final destination. So how does the building site of the future look like? Also here we will see huge automation. Think about the building site of the future more as an assembly line. All the elements delivered to the building site will already carry their logistic and installation instructions. As mentioned before, QR codes and sensors. You can track them until the final destination. With that, we are able to really realize some basic lean principles of just-in-time production and just-in-time delivery. And of course, assembly, as we assemble these things, rather than to construct it on site, it will be more efficient and it will be more safe. And as we produce less waste, it also will be reducing our environmental footprint. There are early examples of this industrialization and modular construction. On the left-hand side, many people will know this 30-story hotel built in 15 days in China by the Broad Group. This was possible because of a high level of prefabrication and optimized logistics. On the right-hand side, you can see modular buildings like the Stack in New York, an apartment house, and a 32-story office building out of modular components. And interestingly, the factory, the prefabrication factory, was built on site to be more effective and to reduce the carbon footprint for an inner city project. But digital fabrication cannot only be used to drive standardization, it can also be used to make very creative ideas buildable, like the Museum of Modern Art in San Francisco, where fiberglass reinforced polymers have been 3D printed and then cut through milling machines. In this case, the 3D printing process was part of the design process. And of course, most of you will know the 3D printed office buildings here in Dubai. Sheikh Mohammed really has high targets, being one of the leaders in 3D printing. By 2030, 25% of all buildings need to be 3D printed, reducing the waste by up to 50% and the cost by up to 60%. Now let's look how artificial intelligence and machine learning can help us on the building site itself. One important example is safety. And safety is one of the major concerns that you hear always when you talk to CEOs of contractors about their main challenges. Artificial intelligence and machine learning can help us there. Let's look to an example of the automotive industry. What if we could use machine learning to discover and react on safety issues in the same way as a car identifies and reacts on objects in the street? Today, construction sites produce more visual content, photos and videos than ever before. With smartphones, drones, on-site cameras, we produce huge amount of visual content. We can use machine learning to turn this visual content into an opportunity to improve safety. By uploading this visual content to the cloud, analyzing it with machine learning, looking to patterns, we can immediately flag problems like a missing personal equipment or an area where air pollution happens. And if needed, we can, of course, directly evacuate the building because every worker wears a sensor and can be informed. The use of IoT, Internet of Things, in a holistic way, with sensors and devices connected to the BIM model in the cloud, enables us to drive and support the construction and operation phase in the whole, with things like tracking objects, optimizing logistics, driving efficiency of hardware equipment like crane movements, monitoring or tracking physical or chemical metrics like humidity of the building or air pollution. In combination with people sensors, we are able to significantly drive productivity and, of course, safety. In the era of connection, we are creating huge amount of information, as shown in this presentation too. But this information is only valuable if we can connect it to people and processes. Connected BIM is exactly doing that, establishing relationships between this data by creating a common data platform where all this information is collected. Everybody, all the stakeholders in the project are able to access this information. Architects, engineers, contractors, subcontractors, facility managers, owners. A single source of truth where every information is stored and possible to get accessed. We call this common data environment. So Connected BIM addresses the whole process from design, fabrication, construction into operations, and is essentially realized by a combination of desktop and cloud services based on a common data platform. BIM 360 is based on Forge, our software development platform and set of APIs that not only allow frictionless data flow, but also have the ability to pass information from one application to another and from one tool to another to establish a single source of truth. The Forge platform is the foundation to build an AEC ecosystem of companies and solutions focused on data access and data integration, not just on the business logic from a single application which is run in isolation. BIM 360 is consolidating all project information to one place. It also removes the issues around data loss because data moves from one application to the other. And it also avoids a big and common problem of design teams that always question, do I have access to the latest information? Net, BIM 360 is the AEC platform and the way to connect you to other teams, to connect you to infinite computing power, to connect you to project data, and to connect you to insights that enable you to realize your projects even better and to contribute to our vision to make a better world. Thank you very much.